Okay, so I just quickly recap where we were last time. So we were considering infinite time horizon dynamic programs or Markov decision processes. So those were Markov decision processes where there wasn't a specific end time. Things could last forever, or they could kind of stop and then cease to accumulate any rewards or losses afterwards. Okay? So here we had a value function which was defined to be the maximum reward over the sets of policies that you could consider, and the rewards were summed from t equals 0 to infinity. Okay? So it just keeps on going. Okay? And for these sorts of cases, okay, it was particularly useful to introduce this notion of a discount factor, this constant beta to the power of t, okay, which just sort of acts like an interest rate that kind of discounts the value of money or rewards in the future. Okay? Right. And then I commented that for this kind of problem, there's a slight difference between when you're maximizing positive rewards or minimizing minimizing positive losses, okay, which is equivalent to maximizing negative rewards, okay. So those are called positive programming and negative programming, and then sort of on the intersection of the two is the idea of bounded programming, okay. And so what we were doing is working through a proof which said that if I can solve Bellman's equation, okay, so even for these types of problems we can write down the Bellman equation just like we had before. If I can solve that, does that mean I've got the optimal policy or not? Okay? So for positive programming, the answer is yes. And for negative programming, it's a little bit more subtle than that, but you can still do something. Okay? So we're just about to finish up the positive programming case. So let's just recall the result. So here we consider a positive program, so that's maximizing positive rewards. Okay, or a discounted program, much of the proof, in fact all the proof works for discounted programming as well. Okay, so given that the reward of a policy is defined, well defined, so it's a nice finite number, okay, and the optimal policy satisfies the following recursion, the following sort of equation, which is this Bellman equation here, okay, alright, and we'd proven that last time. Okay, so we did a sequence of arguments that proved that the optimal value function v satisfies this Bellman equation. Okay, and then we're working to say, well, what if I can find a function r of x that also satisfies this same equation? Does that mean that it's actually the optimal value function? And are the arguments that it maximizes also the optimal sets of actions? Okay, for each state. Okay, and the answer is for positive programming is yes. Okay. If pi is an optimal policy, then the reward function, which that satisfies this Bellman equation, is the reward function of the policy. We proved that last time. Okay, but what we didn't get to do, which we need to finish up, is to prove that that reward function is actually the optimal value function. Okay, is actually equal to this v. Okay, so that's what we're left with doing. Okay, so we're going to do that now. Okay. Are there any questions on that? Okay, so I'm just going to skip forward to where we left off. So here, okay, so now we're going to work towards proving that if I've got a policy pi that satisfies this inequality, or this equality, with equality, then we can show that the reward from that policy is better than the reward from any other policy I like for the first t steps, plus the discount factor applied to my policy from the state that you arrive at. Okay, so here it says if you basically satisfy the Bellman equation, okay, then your policy has a better reward than any other policy pi tilde over t steps. Okay, plus some additional factor. All right. Okay, so let's work towards that. Okay. So what we're going to do is we suppose that policy pi tilde, so some other policy that's not necessarily equal to pi, okay, follows actions a tilde 0 is its first action, then a tilde 1, all the way up to a tilde t. Oh, sorry, it should be t minus 1 here. Okay, so let's suppose those are the first t actions that this policy pi tilde takes, and it does it over these states x tilde 0, which is equal to x, then x tilde 1, all the way up to x tilde t, okay, and that, which is also equal to capital X of t, okay. Okay. Okay, so let's just suppose those are the first things that you do. All right, so just some notation. Then we're going to do the same sorts of substitution argument that we had before. Okay, so notice if I look at the reward from my policy pi and I compare it with the first reward I get from my policy x tilde, okay, which of these two is bigger, this or this? So we've got the reward from R of x, or we've got the reward if I take action a tilde and then I follow policy pi, which is bigger. So who says this is bigger? Who says this is bigger? So one person says it's bigger. Okay, so why is that? Well, because I've assumed that R of x of pi is bigger than the reward from taking any action A, than the reward I get from thereafter. Okay? So I've assumed it here. Okay? And given you've done some sort of homework sheets, we've done some things like this last time, what do I normally do at this point? So now I've made a substitution in here and got an inequality, and then I've got something similar again. So what I'm going to do is do the substitution another time, okay? And I just keep on going, right? So then, this is less than R of x tilde 0 of a tilde 0 plus beta e of x tilde 0 a tilde 0, and then I use the same inequality again, okay, to get R of x tilde 1 and then a tilde 1 plus the expected value given I took action given us at state x tilde 1 and I took action a tilde 1, okay, and then I arrive at the next state, x tilde 2, and I'm following policy pi thereafter, okay. So this is sort of going, I follow pi all the time, policy pi, okay. This is saying I take one action according to policy pi tilde, and then the rest of the time I follow policy pi. It's saying that's worse. Okay? Now this is saying I follow policy pi tilde for the first step and the second step, and after that I follow policy pi. Okay? And you can imagine... Sorry? There should be a beta, you're right. There should be a beta here, yeah. Thank you. Okay, so this would be if I follow policy pi tilde for the first 2 steps, and then I switch over to following policy pi. Okay, and you can imagine if I substitute again, I'm going to get the policy pi tilde followed for 3 steps, and then I follow policy pi from thereafter. Okay, so what I'm going to get here, if I keep substituting in, is I'm going to get the reward that I get from policy from state x0 from following pi tilde for t steps plus beta, beta to the t e of x 0 tilde r of x tilde of t pi. Okay, so as required. Okay, I'm just thinking to myself, I'm not sure if I need a t plus 1 on here or not. I'm not quite sure. I need to double check that. I'll check that later. Okay. Anyway, maybe it needs to be t minus 1 on here. Okay, but anyway, yes, this needs to be t minus 1 on here, and I should probably do a t minus 1 here. Okay, thanks. Okay, so we're kind of part of the way to where we want to be. This sort of says that if my policy pi satisfies the Bellman equation, or is even a little bit better with an inequality here, then it's better than any other policy, at least for t minus 1 steps. Okay, so doing policy pi at the beginning is better than following policy pi tilde at the beginning. Okay? And that's for a fixed length of time t. Okay, so you can probably imagine what I'm going to do if I wanted to have it happening for all time. I'm going to let this little t just go off to infinity. Okay, I'm just going to say, well, actually, as I let little t get bigger and bigger, it's just saying that if I follow policy pi tilde for all time, okay, then that's better than following policy pi. Okay, so that's the next exercise. Okay. All right. So now show that following policy pi is better than following policy pi tilde forever, for all time. Okay. Okay, so let's do that. Well, we've kind of already done it. So we know from the last exercise this is better than the reward at time t minus 1 x pi tilde plus beta to the t e of r of x tilde of t pi. Okay. And now, so one thing you could worry about is, particularly with positive programming, is that this term could somehow have some impact here in terms of the whole sum. Okay, so one way of getting around that is, well, you know it's positive. Okay, so I can just do that inequality. All right. Alternatively, if we were working with discounted programming, this term would be bounded, okay? All right, and this guy would decrease exponentially fast, and so this guy would cancel out. Well, this would grow at most polynomially, and this would decrease exponentially to 0, so the whole term here would go to 0 in discounted programming, okay? Anyway, so we know that we defined the reward over time infinity to be the limit of the reward here as t goes to infinity. So let t go to infinity here, and this goes all the way up to the reward of that policy for all time. Okay? So now we know that if my policy satisfies that Bellman recursion, that Bellman equation, then it's better than any other policy. Okay? In other words, it has to be optimal. Okay? Because if the reward for my policy is better than any other policy pi tilde, then it has to be optimal. Okay? So okay, and that's it. Okay. So you can notice we've really been using the kind of same steps over and over again, with slight perturbations to them, slight changes, but nothing too big. But essentially the main idea is just repeated substitution of Bellman's equation into itself. Okay? We've kind of seen that quite a few times now. All right? Okay, so we're just kind of unraveling the kind of Bellman equation to get that kind of tree shape that we had earlier. Okay? So just going back. So now we've just proven this last step. We said that if the policy, okay, satisfies this equality or inequality even here, okay, so something slightly weaker assumption, okay, then we have the value function, that the policy is equal to the value of the optimal value here, okay? Right? So it's bigger where V of x is defined to be the optimal policy amongst all policies, okay? All right. Okay. So that's the positive. Oops, sorry. That's the positive programming case. Let's do the negative programming case. Okay. So the proof isn't too much more. Okay, but I want to understand a little bit why negative programming involves a slightly different statement here. Okay. In fact, I think I gave in your examples sheet, your exercise sheet, the last exercise gives an example of a value of a function, a reward function, or a cost function in this case, which satisfies the Bellman equation but isn't optimal. Okay, so you'll see it in an example in the course, all right, of a kind of stopping problem where satisfying the Bellman equation doesn't imply optimality, and that's because it's a negative program. Okay, we can't guarantee that solving Bellman's equations for negative programs implies optimality of the policy. Okay. So we have to be a little bit more careful how we state things, okay? So here we see an analogous result to theorem 1 that we just proved for positive programming, but for negative programming, and is much weaker. Well, it's not to say much weaker, but it's certainly a weaker result. It's not as strong a statement as we can make for positive programming. Essentially, we apply the same idea of, well, essentially the reason it happens is that original exercise that I showed you, which I think was exercise 4 here, that negative programming sort of increases and then overshoots the optimal value. We kind of need to bring it back down again. Whereas remember that we said that sort of the positive programming, whenever we increase time, it increases the overall reward, and whenever we increase the reward of a policy, it increases towards the optimal value. Whereas with the negative programming, it tends to kind of overshoot as we increase time, have to bring it back down by getting better and better policies. Okay, so that's the kind of main reason why negative programming kind of has these issues. Okay, right. So the first question is kind of a trivial one. So consider a Markov decision process with a finite number of actions and assume that the Bellman's equation has a solution. Show that there is a policy solving the Bellman equation. Okay? So, sorry. So the answer to this isn't too hard. We basically have our Bellman equation. that the loss, optimal loss from action X, is equal to the minimum over the sets of actions A, okay, over the losses, okay, of taking action A, and then the loss from there on after. Okay. So now, well, if there's a finite number of actions here, there's always going to be one that's minimizing it. Okay, so if I take L, the optimal value function, okay, I know, and I take the Bellman equation associated with it, there's a finite number of actions in here, so I can choose the one that minimizes it. Okay, so take pi of x to be the argmin, so the argument minimizing the sets of actions here, Lx of A, okay. This defines a policy, okay, that satisfies Bellman's equation. All right, I noticed I skipped ahead a little bit here. So one thing to say is it's actually something, when we have for each state X, an action that we choose by our policy, pi x, then it's called a stationary policy. So I'll just highlight that. So a policy, pi, is called a stationary policy, okay, if its action only depends on the current state, okay? So it doesn't depend on any randomness, and it doesn't depend on time, it doesn't depend on the history, it just depends on the current state that you're at X, okay? In fact, most of the time it's better to think of the policies that you come up with from an infinite time horizon Markov decision process as being stationary. You just go, well, I'm in this state, let's just make the action that's best in that state, okay? We don't need to say, like, the second time I'll take a slightly different action or anything like that, okay? We'll work with policies a lot more like that in the next section when we have some sort of algorithms for this, okay? Okay. So you can kind of see the two ingredients that we're going to be assuming here, okay? Typically for negative programming, people assume that policies are stationary, and typically people assume that the policies have a finite number of actions as well, okay? Okay. So here's the main result. This is sort of the alteration that we have of theorem 1, which we proved for positive programming. So let's just read that through. So consider a negative program, okay? That's where we're trying to minimize positive costs or positive losses, okay? Given that the limiting cost function of a policy is well defined for each policy, and I should apologize for a slight typo there. That shouldn't have a T on it. And I'll also apologize in advance for a slight typo that happens. Sometimes I use little l of x of a for loss, and sometimes I've been using little c of x of a for cost, and I'm a little bit ambiguous. So little l is equal to little c for all of this section, okay? So I think I'll try to stick with L, so that should be little l, okay? So for the rest of the time I write the proofs, I try to write little l for the kind of instantaneous loss. Okay? Okay. This is what happens. I've just written these notes for the first time, so there's all these little bugs that need kind of fixing up. Okay, anyway. So let's go about proving this. Okay. So, yeah. Sorry, I'll finish stating the result first. Sorry. So, consider a negative program. Given that the limiting cost function is well defined for each policy, the optimal policy L, okay, so the best value function, okay, or the lowest cost that I can achieve, which is given by L of x, satisfies the Bellman equation again, okay? So if I minimize the cost over all pi and get this value L of x, it satisfies the Bellman equation. That's the same as before, okay? Moreover, any stationary policy that solves the Bellman equation, okay, so solves this, is optimal, okay? And the one thing to highlight here is notice that I've assumed that this is the optimal value function in here. I haven't put in some other function. You need to have sort of found the optimal value function first and then check that the policy that you come up with satisfies this in order to get the optimal policy, okay? So before, I could just take any function like r, and it had to satisfy this. It didn't need to be the optimal value function. I just need to find something that solved this, and then I could do this bit. Okay? Now, I actually need to have found the optimal value function L, okay? And then the stationary policy associated with it is going to be an optimal policy, okay? So it makes the task a little bit harder. Before, I just need to solve Bellman's equation, okay, and then find the policy associated with my solution, and that gave me an optimal answer. Here, I've got to find the optimal value function first, that L of x, and then find the stationary policy associated with it, which is a little bit more difficult task, okay? Right, okay. Are there any questions about that? Okay, much of the proof here is going to be very similar to before. Okay, so there's nothing too big a change here. All right, but I'll just quickly go through it. In fact, we've actually done a lot of the arguments so far. So I'll go through the proof. So the thing to say is that I'll do the answer here. So 1. The Bellman equation is solved by L of x is exactly the same argument as for positive programming. That's something that doesn't change when we go to negative programming, okay? So showing that this holds is exactly the same thing. You can go through exactly the same steps that we did for the positive programming case, and we can get the same inequality, the same equality here, okay? All right. All right. So what about this last bit? Okay. So the argument here goes like this, to show that if I found the optimal value function L, and if I find a stationary policy that satisfies this, then this is actually going to give me the optimal policy. Okay, so once I've got the value function, I can also get the policy out of it. Okay. Okay. Okay, so, and it's basically the same idea as before. We just repeatedly substitute this sort of Bellman recursion into itself, okay? So notice that L of x, we know, satisfies this equality. Okay. Then we can say, well, I don't need to choose the minimum over all the actions because I've got one specific value, pi of x, which achieves this minimum. So I'm just going to substitute that in. And note there's no inequality here, it's equality. That's important. That pi of x. Okay. So now what I've got is I've got that the optimal value function is equal, has the same value, if I take one action according to my stationary policy pi x, and then follow the optimal value function. Okay? So the one move with this policy pi is the same as the value function. So it preserves the value. Okay? All right. Then, what do I normally do when I get to this state? What did I do before? Sorry? Yeah, substituted it in again. I just keep on going, substituting it, okay? So now I can put in L of x of pi. Oop, should have a hat on that x. Pi of x hat. So that's the first state visited by my policy. I'll put a 1 on it. Plus beta squared, or just 1 beta, e to the x1 pi of x1. Sorry, capital L of x hat 2. Okay. And now, again, I've got the loss from my policy pi over 2 steps, then beta squared times the expected value of the optimal policy from there on out. Okay. So notice that this guy here, again, is really just equal to the cost over 2 steps from x of the stationary policy pi. Okay? So a little bit like before, right? And as you can guess, if I keep substituting, okay, I'm going to get the cost over, say, t minus 1 steps of x of policy pi plus beta to the t e of x of the loss of the state reached by my policy pi after t steps. Okay? Then I do something very similar to what I did before. I say that this is a positive number. That's less than the cost at this point. Okay? And then I let t go to infinity again. Okay, and it's going to converge to the cost function associated with my policy pi. Okay? So then the cost of policy pi is less than or equal to the optimal cost, so it has to be equal to it. Okay? Okay, it's inequality here, but remember this is the minimum over all policies. So if I found a policy that's small, it has to be equal to it. Okay, that's it. All right, so very similar to the previous argument. Okay, I have to be a little bit careful. Okay, so the issue was before I could get away with these being inequalities here. Now I have to be a little bit make a slightly stronger assumption so I can keep these equalities the whole time through. Okay. Okay. Right. Are there any questions about those proofs? Okay. So there are kind of two proofs there. That's kind of more theoretical part, the way we're going to do things. So next I want to do one example. Okay. So how are we doing for time? Yeah. Next, after the break, I'll do one example, and then we'll go on to do algorithms for these sorts of problems. Okay. Great. Thanks.